What's up, guys? Let's talk now about the Dahmköhler number. And probably you're asking yourself, what's this? Or where do we got this? Well, first of all, it's a dimensionless number. So probably by far or by now, you should recognize the Reynolds number, Grashof number, the Nusselt number, I don't know, other numbers, and the Prandtl number. These numbers, they are relationship, and you can find them experimental. They go when you do especially momentum transfer, heat transfer, mass transfer, all those kind of operations, you will find them. And you will also find one or many, or at least this one, Dahmköhler one. And what you know that Reynolds is essentially the how to measure flow rates, Prandtl is how heat transfers, Nusselt is for the heat coefficient, etc. So Dahmköhler number is essentially a quick estimate to know the degree of conversion, or how far or how big can you get the conversion. So having Dahmköhler numbers, you can easily just know that that reaction could go further or get better if you have low rates, or if you have low rates of conversion, you will understand that it's because it has a special Dahmköhler number. So by definition, it's the ratio of the rate of reaction at the entrance, that's very important, versus the entering flow rate of A. Yeah, I know it doesn't make that much sense, but there's also another definition, I think it's the good one. Also, it's also the ratio of the rate of reaction, that means how fast is reacting per unit volume, per unit time, of course, versus the convection rate, that's how much are you entering. So by definition is that here. How much rate of reaction is how much moles per unit time per moles per also unit time. They need to cancel, moles go out, times and times. The only difference is that this is a feed or an inlet, and you're comparing it with a reaction. So maybe right now it doesn't make that much sense, but we're going to use it, and you will start getting how to use it, why is it makes sense, how can we use it in other exercise, and so on. Now let's apply the Dahmköhler number for a CSTR of first order. Of course, it's only one CSTR, one reaction. So by definition, we got this here. That's the Dahmköhler number. Let's do an analysis in a first order reaction. So this is here, let me say, yeah. This is my design equation, and you get this. And you will find out that, for example, well, wait for it, the Dahmköhler number is here, yeah. Rate of reaction at the inlet is this here. The volume stays the same, this is the volume. Now, by definition, the volumetric flow rate at the inlet times the initial concentration, these two guys, is this here. So I just substituted data. First order, it's K times concentration. Now concentration goes away, Important to note that it's initial concentration, guys. And we are left with K, the constant or reaction constant, the volume, and the volumetric flow rate, which this is, we know, is space-time. So that's very awesome. Dahmköhler number for a first order reaction, CSTR, equals K times tau. That's cool, and we are going to actually use it later. I also included second order because it's also common to have second order. So the Dahmköhler number equals the rate of reaction here at the inlet times the volume divided by FaO0, which is the inlet. Now, let's substitute this here. We know that the rate of reaction for the second order is this thing I just circled. K times Ca0 to the square root, to the second power, sorry. The volume stays the same. Once again, we know the volumetric flow rate and the concentration at the inlet. So we just cancel this one with this one. Since it's the second power, it goes to the first power. K stays the same, the volume stays the same, and the volumetric flow rate stays the same. Once again, we order this to get tau. Tau is spacetime. So the Dahmköhler number for the second order reactions is almost the same, but you got the Ca0 here. And actually, I am a great fan of finding the nth for the case you need a 5th order or 5th order or 0 order. Let's see if we can generalize this. You can verify it by yourself, do it by yourself alone for 0, for 3rd power, for 5th power, and then you try this here. I got that the Dahmköhler number for the nth, let's say, order will be the constant here will remain constant. For example, KCA0, which was the second order. The first order was K tau. And what else do we have here? Well, Ca, or initial concentration, to the n-1. So if we got n equals 2, second order, minus 1, we will get 1. And it's the case here. So it's, at least for the first order and second order, they apply. So I told you before that we could know how well will perform an equation or a reactor. Let's introduce you to this rule of thumb of Dahmköhler number. And I say of thumb because it's not a super rule or a perfect heuristic or it's always happens. It is just a rule of thumb in general. You will need to do your analysis, but for very quick estimations or very fast, it's okay. If you're talking with your boss and of course you don't want to take out your Aspen computer or your programs in Excel or look at all the data, you just tell, oh yeah, what's the Dahmköhler number, you find it, and yes, it's a bigger than 50% conversion, or at least more or less. Sure, if you're going to design it, you're not going to just make this rule of thumb, but for the moment, it's okay. So, if the Dahmköhler number is bigger than 10, the conversion may, and I write this may, it doesn't mean that it will, or it needs to, or it will happen. It's just it may. It's common, or it will be acceptable that you can achieve at least 90%. So if you have a Dahmköhler number of 50, you are expecting to have a high conversion. You have a low conversion, you should check out why, because I told you before, it's only the case that you could have that number. It doesn't mean that you will have that number. So yeah, let's keep going. Dahmköhler number lower than 0.1, the conversion will be low. That means maximum 10%. And what does that mean? You need to improve your Dahmköhler number. And many times you will not be able to improve it, because maybe you make it high, but I told you once again, it's only a may, it's not a must. It will not, like, this is actually wrong. It's not a will, it's a may or might happen. So yeah, you're probably wondering, yeah, Dahmköhler and conversion have a relationship? Yes, they have. For the first order, let's remember this equation. We found out this. And just to let you know, this is my little Dahmköhler for first order. So substituting here, we found this very interesting equation. And well, we'll be using this further, this number, the Dahmköhler number, in the CSTR for first and second order, especially for further analysis. Actually, the next video talks about that. Help us analyze faster and easier. That's cool. That's why we introduced the Dahmköhler number. Maybe it doesn't make sense to you, but it does help us to do it. And especially if we are analyzing in series or parallel CSTRs, we will be analyzing especially the size, temperature, conversion, all that. It's very good or very convenient to do it with the Dahmköhler number. And I think we're done. Actually, let me give you a small peek for the next topic, which is CSTR in series. Yes, I know we've seen that before, but we're going to talk about in terms of Dahmköhler and not only first order but many other. So keep watching, guys. See you in the next video. What's up, guys? It's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. Thank you guys for the support and the love.